Okay, so this video is going to be it's going to show how to use Boyle's Law. So we're going to get a little bit more. We went over the Boyle's Law real quick last time. We're going to get a little bit more closely um, related to Boyle's Law, or uh, acquainted better with Boyle's Law. So, excuse me. We talked about Boyle's Law as showing the relationship between volume and pressure, and you can go ahead and take a gas and change its volume and then measure its pressure, and you'll get what's called an inverse function, where it kind of goes down and but never actually reaches the x-axis as you go to the right on the x-axis. And if you continued to the left, the y-axis would climb, but never actually reach the y-axis. And so uh, what's good about that is that it tells you that these are inversely proportional. As x gets bigger, y gets smaller. As x gets smaller, y gets bigger. But it doesn't give us an equation. We need an equation. So what they did is they said, all right, well, whenever we have an inverse proportional, what we could do is we can plot the pressure on the y-axis and the inverse of volume, 1 divided by v, on the x-axis. And when you do that for a inversely proportional relationship, you get a direct relationship. So the pressure is directly proportional to the inverse of volume. Hopefully you remember this from algebra. But what that means is that you get a straight line. And scientists love straight lines. You know why? Y equals mx plus b. Yeah, you thought you'd never use that outside of a math class ever again, right? It's used in finance, it's used in science. We use it all the time. If you get a straight line, it's magic, it's gold, because you know what? You could make an equation out of it. You know what? Because we know y equals mx plus b. So on your y-axis is pressure. On your x-axis is the inverse of volume, 1 over v. So we can plug it into our y equals mx plus b. And so in order to calculate an equation for Boyle's law, the Boyle's law relationship. In other words, an equation for Boyle's law. Instead of writing y equals mx plus b, what you write is, instead, in place of y, you put a p. That's what was on the y-axis, right? The y-axis is pressure. On the x-axis is 1 divided by volume. So instead of y, you put a p. Instead of x, you put 1 over v. Now, scientists are these people that well, mathematicians like using m for slope. I don't know why. Scientists, m is mass. So we like to think of a slope as something that's constant. So they use the letter k. Okay. Why k? Why not c? Well, that's even more complicated, but basically has to do with the fact that c is already taken by the speed of light. So a lot of times we will use constants k. K is a constant. So p, which is your y-axis, equals to k, which is your slope, times 1 over v plus the y-intercept. And in this case, the y-intercept, in just about every case, the y-intercept here is 0. Actually, it turns out that all these lines go through the origin, 0, 0. So remember that y-intercept is, where does b is the y-intercept. The y-intercept is, where does your equation go through the y-axis, and it is at 0, 0.0. So we can get rid of that. So it leaves us with p is equal to k times 1 over v. Now, we don't like equations with denominators if we can get rid of them. So multiply both sides by v brings the v onto the left side, right? Multiply v on the right, and that's going to cancel out the v's on the right and leave me with p times v is equal to k. What that tells me is that whatever pressure I put in there from any of my points, order pairs, I'm going to have a v that is equal to some constant, some number k. Right. So if at one point in time I have a pressure and I have a volume, we'll call it P1 and V1. If I multiply P1 times V1, I get this constant. Now, if I change the volume and it changes the pressure, so now it's a different pressure and a different volume. So it's at some second point in time. That's why I call it P2 and V2. Then we'll call it P2 times V2. P2 times V2 still have to equal to K. So whatever the K is, because the K is going to vary from gas to gas. But once you have one sample of gas, that K is always going to stay the same. So P1 times V1 equals to this constant. P2 times V2 also equal to this constant. And once again, this constant is only constant for that sample of gas. It'll be a different constant. It'll be a different number and a different sample of gas, probably. But since both of them are equal to the constant, they have to be equal to each other. And so this is our workable form of Boyles law. P1 times V1, your first pressure times your first volume, equals your second pressure times your second volume. And once you have Boyles law like this, you can then go ahead and solve questions like this. A gas is initially at a pressure of 1 atmosphere and occupies a volume of 340 milliliters. What is the final pressure of the gas if it is compressed to 190 milliliters? So we're going to do a sample problem with that one. So let's go ahead and do that. Let me go ahead and go back over here to web whiteboard while we still have it. First off, real quickly, just to kind of go ahead and go over this real quick. So I have P1 times V1 equals to P2 times V2. We can use this when temperature is constant. Temp is constant. In other words, T1 and T2 are equal to each other. They haven't changed, but P1 and P2 aren't. Now, real quickly, just to kind of point this out. All right, so this is one variable. P1 is one variable. V1 is one variable. You don't do anything with these numbers. They're just subscripts. I'll tell you, this is the first pressure versus the second pressure. P2 is the third variable, and V2 is the fourth variable. Okay. So just pointing that out so that you guys know that these subscripts are just numbers to differentiate the different pressures and the different volumes. You don't multiply, divide, or do anything with them like you would when you're calculating atomic mass. Okay. All right, so let's go ahead and get to that problem here. The problem, once again, was gas is initially at a pressure of 1 atmosphere and occupies a volume of 340 milliliters. So we have a gas. We'll say that is initially, so that means it's P1. Let me change the color back here. P1, I need a pen too. P1 is equal to 1 atmosphere. V1 is 340 milliliters. And the volume units don't matter as long as you, and even the pressure units don't matter, as long as you use the same ones for P1 and P2 or V1 and V2. So it's at 340 milliliters. What we do is we compress the gas, so we made it smaller, to 190 milliliters, and we're asked what is the final pressure. So what we're going to be doing is looking for P2, right? P2 is what we're looking for, and we have a V2. V2 is 190 milliliters. So we have a P1, we have a V1, we have a V2, and we're looking for P2. They say that if you have all the variables but one, if you're left with just one variable, you can solve for it. And so that's what we're going to do. We're going to plug in. P1 is 1 atmosphere. V1 is 340 milliliters. So this is P1. Then this is V1 equals to P2 is what we're looking for. So I'm going to leave this as P2. And V2 is 190 milliliters. I'm putting the brackets so that, or the parentheses, so that we can kind of differentiate them. And once again in blue, what I'll do is I'll remind you this is P1, this is V1. We're multiplying them together equals to P2 here, which is what we're looking for, times V2. And all you do now is plug and chug and solve it. Now, I know some people this is easy for them, and hopefully it is, but for other people, they need a reminder how to do this. All right, P2 is being multiplied by 190 milliliters. So in order to get it by itself, we need to get rid of the 190 milliliters. We want P2 by itself. You want to isolate the P2. So divide both sides by 190 milliliters. By doing that, now you cancel these two out. And that leaves P2 by itself. But if you just divided the right side by 190 milliliters, you have to divide by the left side by 190 milliliters. And so what you're going to do in order to figure out what P2 is, you're going to take the 1, multiply by 340, divided by 190. And what I'm going to get is, let me get my calculator out of here. I'm getting my calculator. I don't have my camera on tonight because I haven't fixed myself up. I just showered and ready almost for bed. So 1 times 340 divided by 190. Let me go ahead and do that. It's going to give me 1.79. 1.79. 1.79. And notice that the milliliters here cancel with the milliliters here. The only thing that's left is units are atmospheres, which is appropriate for pressure. Right? If you had been given the pressure in kilopascals, then you would have ended up with kilopascals here. Or if you would have given millimeters of mercury, you'd end up with millimeters of mercury here. It'll work always. Okay. And also notice that this follows that Boyles Law whole thing. If volume, let me go ahead and use screen here. What happened to volume? It went down. All right, it went from 340 to 190. It went down. Our pressure ended up at 1.79 atmospheres. So we were told from Boyles' law that if your volume goes down, your pressure is going to increase. And it did. It went from 1 atmosphere to 1.79 atmospheres. So as volume went down, pressure went up. Followed Boyles' law. And that's how you would do the problems. And there's your answer right there, 1.79 atmospheres. So you can predict what the pressure will be. Okay, and that's all you do. You could use, you can be given a problem where P1 is your variable, V1 is your variable, or V2 is your variable. Any one of these can be your variables. So in this case, P2 was what we're looking for. As long as you have the other three, you should be able to solve for the fourth one. Okay. All right, that's all for this video. I'll have another one on Charles' law and Gay-Lussac's law on the combined gas law.